Good evening, everybody. First of all, wish you all a very happy Diwali and healthy new year ahead. Welcome to the IPA50 webinar series, New Horizons in Physics. In this series, we are trying to bring you different facets of physics and exciting research problems of the present era. Today, we have Dr. Nayak from BARC, who will tell us an interesting story of fusion and fission. And to coordinate today's lecture, we have Professor Bibhas Behra from Punjab University. Professor Bibhas Behra himself is a nuclear physicist working in the area of fission, particularly of heavy nuclei. And I now invite him to coordinate this lecture and introduce today's speaker.
Okay, thank you, Bandana. Dear all the audience, we wish you a happy Diwali. And we are privileged to have Dr. B.K. Nayak as today's speaker. So Dr. B.K. Nayak, he is well known in the nuclear physics community of the India. He was born in Odisha and did MSc from the physics department of Banaras Hindu University, Varanasi. Soon after finishing his MSc, he joined the Bhabha Atomic Research Center Training School programs. After successfully finishing the program, he joined as a scientific officer at the Nuclear Physics Division of the Bhabha Atomic Research Center. At Nuclear Physics Division, actually he nurtured himself in experiment to become an experimental nuclear physicist in the specific area of heavy ion reactions around the Coulomb barrier energy. At Nuclear Physics Division, he started his careers with the Indian nuclear physics stalwarts like Professor S.S. Kapoor, Professor V.S. Ramamurthy, and Dr. R.K. Chaudhary. He has extensively carried out research in the heavy ion fusion fission and surrogate reactions, among many other reactions. Particularly in the last decades, he has contributed in a significant way to the surrogate reactions methods in nuclear physics. And he had the distinction of being the head of the fission physics division of the nuclear physics division. And this fission physics division is well known in India and also in the world for the basic fission physics research. Dr. Nayak has co-authored more than 150 research papers to his credits, out of which almost around hundreds in the American Physical Society Journal, that Physical Review C and Physical Review Letters. He is the recipient of the Homi Bhabha Science and Technology Award of the 2009 for his significant contribution to the nuclear physics research by the Department of Atomic Energy. He was also the Associate Director of the Physics Group and also the head of the Nuclear Physics Divisions, Atomic Molecular Physics Divisions, High Pressure and Synchrotron Radiation Divisions of the Bhabha Atomic Research Center before his superannuation in the month of June 2020. For a significant years also, he was the Dean Academic Physics and Mathematical Science of the Homi Bhabha National Institutes situated inside the BRC. And Dr. Nayak is very well known to nurture the young physicists, and he has guided many PhD students and many young scientific officers at the BRC. And he was very helpful in helping the young physicists in nuclear physics. And today he will be talking about one of the research areas which he has spent significant times at BRC, that is the portrait of the nuclear fusion fissions from basic research to applications. Now I hand over the screen to Dr. Nayak. So please, Dr. Nayak, you can start.
Thank you, Bibhas, for generous introduction. And at the outset, let me also join you in wishing everybody a happy Diwali. And also I thank IPA for giving me this opportunity to speak on some of the research work I did before I superannuated. And today I will be speaking on fusion fission reaction from basic research to application. Let me just load the screen. When you talk about fusion fission, it looks, in our school level student study. So it's a very, in that sense, very old topic. But what I'm going to show you all is that though it is fission is discovered some more than 80 years back, still it has not been really a properly, there is any theory which can really tell about tell all the aspect of fission. And still we are trying to understand various aspects. But in the meantime, lot of application has come up as a research to understand the basics of fission. It has given rise to a series of applications that also I will try to highlight in today's lecture. Okay, let me just tell you something about history of nuclear fission. Actually, after the discovery of neutron by James Chadwick, sometimes in 1932, Enrico Fermi wanted to extend the periodic table. So he started experiments in 1934 in Rome, where he irradiated uranium-238 with a neutron. And he concluded that his experiments has created new elements with the Z is equal to 93 and 94. In 1938, Fermi was given Nobel Prize for this work. But however, not all were convinced by Fermi's analysis of his work. Otto Hahn and Lisa Meitner and Stressman Berlin group started doing radiochemical analysis of freshly separated purified irradiated uranium solutions in Berlin and published several papers supporting Fermi's result. Meitner, in the meantime, left Berlin to escape from Nazis. She fled to Sweden, and only through correspondence he was talking to Hahn. Hahn in Berlin observed chemical signature of barium and wrote to Meitner. It was surprising to them, but was very they were very confident that Hahn, as a chemist, cannot go wrong. Subsequently, by measuring the energy of the fragments using ionization chamber, it was confirmed to be fission by Meitner and Fresh. So this is the work by Otto Hahn and Stressman. That is Nature paper 27, 1993. That gave them Nobel Prize in 1944. And it was Lisa Meitner and Otto Frisch. They only identified fission fragments, and they also gave the first simplified model adopting Bohr liquid drop model of the fission. So the early understanding of fission process was basically liquid drop, because they were seeing that it breaks into two parts only. It's not breaking into many parts. So those days, even this binding energy also was available, and from the binding energy formula, they could see that they could show that surface and Coulomb energy can change while as a function of deformation. When you surface energy will increase, but Coulomb energy will decrease. This will give a barrier for all the elements basically beyond iron. So all those elements beyond iron, basically they are stable because of this barrier, and fission is basically overcoming this barrier. And subsequently, led to the conclusion about the chain reaction. Uh, and if I just chronologically write down how from basic research this it has gone to technology in year wise, you can see here. It was Newton was discovered in 32, 33 discovery of nuclear force, 34 discovery of artificial radioactivity, mass and binding energy formula was known by 35, 36 compound nucleus, 37 liquid drum model, 38 theory of energy production in stars. That is that fusion was understood in 38, and fission of uranium 39. Idea of fission bomb came so early 39. Once you know that idea of chain reaction when it was there, then 41 discovery of new elements by irradiating. Then immediately the technology front, the Manhattan Project started, construction of isotope separation, Fermi nuclear pile, and as you all know, nuclear bomb, 1945. 48, it was the first time electricity generated by a nuclear reactor at Oak Ridge that was shown. So I don't think any other branch of science where your basic research has gone to technology in such a short period of time, maybe 16 years. But then, this is all about, okay, we have fission, we know that we are producing nuclear energy, and also, it has got application in medical and agriculture, all aspects of life now. Nuclear program is helping the mankind. But still, then what we are doing? You remember the first thing what Fermi was trying to do? He was trying to, extend the periodic table. That problem is still remaining. So, but very soon it was realized that maybe with the bombardment of neutron, you cannot go to very high jet very higher elements. So then it was concluded that maybe by fusion reaction, you can go to see the newer elements. You can explore the this periodic chart, because as you know, we have only 300 stable isotopes, and there are supposed to be almost like a 7,000 elements in principle. And then then how do we explore this? This only gave the impetus for heavy research around Coulomb barrier. Of course, there are two philosophies that is being implemented now. One is cold fusion, and other is called hot fusion. When you are using cold fusion, you try to populate the compound system at minimum excitation energy, so that just 5 to 10 MeV above the your excitation energy. But there is other school of thought, what is called the hot fusion path, where you take actinide targets and populate the compound nucleus at a very high excitation energy. But this nucleus being it's not a liquid like a water. Immediately it snaps out. It's a more like a honey. So because of this dissipative nature of the nucleus, it really takes time to undergo fission. In the meantime, suppose neutrons are emitted, then you can cool down the system and you can form the super heavy element. So these are the ideas they have been being pursued, and I can just say that the primary aim of current nuclear research around Coulomb barrier is basically to understand how this we have these heavy elements, how to produce, and how why we have only limited number of elements. Why not with the highly neutron rich and proton rich? What is the thing that is limiting production of heavier and heavier elements? So when you want to address this question, you have to understand what is called fusion fission dynamics, because this evaporation, so super heavy element evaporation residue cross section will depend on three parts. One is capture, then a probability of compound nucleus formation, and this is the survival of the compound nucleus. So capture probability is more or less understood. This will depend on the Coulomb barrier, and the survival is also compound nucleus decay fission probability, that is also known. What is more interesting is this dynamical part, probability of formation of compound nucleus. But what is happening when instead of compound nucleus, there are new um, uh, channels like quasi fission, fast fission. They are being opened up. Though you from your capture you will say that I should have so much burn of compound nucleus cross section, but really you will get less. So most of the research is now is going on to understand how for different internal parameters uh, how to optimize, how where you can get maximum probability for reaction P dynamic. So here there is a pictorial I have shown here. What it is showing, a projectile is coming and getting captured. It makes a uh, dinuclear system, and if it is instead of really forming a equilibrated compound system, it breaks, then it is, you call it quasi fission. And or if it is going to a compound system and then fissions, you call it fusion fission. Or if it is then if it is still remaining, then you call it evaporation residue. So in a compound nucleus, usually it is two-step process. One is what is called it is governed by the formation of governed by the entrance cell, leading to formation of a compound system. And the second is once you have form a compound system, it forgets completely how it is formed, and it's totally it forgets its entrance channel. Whichever way you form the compound system, its decay will be independent of formation. But when you talk about heavy ion induced fusion fission reaction, things are different. Here, heavy ion induced reactions, there is strong entrance channel effects has been observed. Some of the entrance channel parameters are entrance channel mass asymmetry, ZP, ZT, deformation, facility, and cell closure. And it has been observed that there is a some of the observable is a low evaporation residue cross section than what you expect, higher fission fragment mass width than what you expect from a purely compound nuclear case, and higher fission fragment angular distribution, and low precision multiplicity. Because of these effects, these are the observables. Now we'll see how in the past we have seen this type of effect in heavy and induced fusion fission reactions. This is one of the very early result I'm showing. This is one of the first experiment of pelletron, where you see there are oxygen and thorium, then carbon and thorium, and boron and thorium. Boron and thorium and carbon and thorium, they very well match with your statistical model prediction. But as you go to oxygen, there is a deviation. And here also, with a neptunium target, you can see. So same thing, you can say what is called the mass symmetry or alpha. At to certain alpha, you see you match with the statistical model, but beyond that it deviates. So these are like the mass asymmetry entrance channel effect was shown in one of the very early work from pelletron. Subsequently, also, even if your projectile or target has got spin or no spin, that also shows a different anisotropy when you go to below barrier energies. So ground state spin also affecting your anisotropy. Here I'm showing one case where your projectile has got deformation, but target is spherical. Here you don't see at lower energy there is no deviation. But if your projectile is deformed, but if your target is deformed, then you see for a silicon and boron, you see in a case of boron, you have filled squares, there is no deviation, but when you go to silicon, there is a deviation. So these type of effects were observed, and these observations has been subsequently been explained using maybe qualitative and phenological models, where you have shown that depending on the extended contact configuration, your BG point, what is called mass asymmetry, Bijumura-Galvan point, is shifted. That means what it says, that suppose your BG point was here and your system was left side or right side, it behave in a certain way. But if your contact point is 0 or 90, then your BG point can change. So that way, though you start with your system was alpha was greater than alpha bg, but now depending on orientation, it is now less than alpha bg. So but in all the cases, normally when alpha is greater than alpha bg, you should see a compound nuclear reaction. But because of this dynamical change because of the extended configuration, you can see the pre-equilibrium component also. In other case also, using this type of a model, subsequently, most of the experimental data or anomalies in fission fragment anisotropy has been explained. Then when you come to mass fission fragment mass distribution, here it is shown for Newton-induced. In case of Newton-induced fission fragment, mass distribution is always asymmetric, and this has understood as due to cell effect, because for any, you see, for a series of actinides, Newton-induced fission cross-section mass distribution is given, where your heavy mass is remaining at one point around 140. Only light mass is changing. So it is understood because it is due to cell effect, because around 140 you have a cell closure, and so this has been shown through a multi-dimensional potential surface. So you have for these systems, you have a potential surface in such a way that it always takes it to asymmetric configuration. Now you see, understand, we started with a liquid drop model, but in liquid drop model, this microscopic effect were not included. So one of the improvement that over the year has come is basically this multi-dimensional potential surface of the fission. This is something new. But once you say that cell effect is very important, but there was work on mercury 180. If our only the projectile cell effect would have been the most important factor, then for 180 mercury, we should have seen a symmetric peak, because mercury split into 90. So 90 means 50 Newton number and 40 proton number, that would be zinc. Then we should have seen symmetric fission. But experimentally, you see the asymmetry. So that means it's your this multi-dimensional potential surface is requiring something more than just a cell effect. So subsequently, one of the, as I told, the new development that has taken place over the year in fission is, I think, this multi-dimensional potential surface calculation, where you take 5 degrees of freedom. One is elongation, and then mass asymmetry, and deformation of each fragment, and the neck degree of freedom. With this type of calculation, one can see, depending on the trajectory of the collective motion, the nucleus, the potential energy surface, you can see deep inelastic, or you can see quasi-elastic fission, or you can see fast fission, or you can also see this compound nuclear, and then fusion fission. And these are some of these experimental observations. So here you see you are forming two compound system. One is with magnesium and cadmium, and the other one is sulfur on uranium. You see, they are forming the same compound system. But in one case, your compound nuclear formation cross section is so much, and other case it is low. So this is these are the what is called the your reducing the compound nuclear cross section for super heavy element production, because this international is very crucial here. As I told you, we have a potential surface. Multidimensional potential surface. As you go down in energy, you should see the effect of potential. That is what exactly is seen here. You see, you are seeing a single peak, but as you go down in your barrier energy, you see, quasi-elastic contribution. But these are shaded region is what is expected from a pure compound nuclear case. And you see, for last few years, there has been a large number of studies just to understand how this fission fragment mass distribution are there in this NZ plane. So because it's very sensitive, as observed, are very sensitive to neutron and proton number. So a large number of study is there. And just to understand more deeply this, particularly the quasi-elastic fission, and it has been really grouped into three types. One is what is called, you see a mass and angle correlation, that is called mass angle distribution, highly correlated. That means if it is a very short time, it splits, it separates, then it will see a very high correlation, mass angle distribution. So you'll see a basically a U-shaped mass distribution. But then in a middle case, when it splits after maybe half a rotation, then you see a strong correlation of mass and theta. And in other case, if it is taking almost a one rotation then splitting, you don't see any mass angle correlation. So only what you see is the broad mass distribution. So in a recent one of the recent work, so what we wanted to see that how this cell closure that is affecting this quasi-fission. So we took the reaction 35, 37 chlorine on lead 206 and 208, just because lead 206, 208 are spherical. So what we did, they are called the magicity number. That means in case of chlorine 35 plus lead, your lead proton number is cell closure, but none other is a cell closure. So you give number 1. And then chlorine 35, then 208 lead, you have both proton and neutron number are cell closure here. So N is 2. In this case, here Newton number, here Newton number. So N is 2. In this case, Newton and proton number, and here the Newton number. So N is equal to 3. So most of this, all this reaction, what was observed, that we don't see any mass angle correlation. But if you see from the facility point of view, as it has done in earlier works, facility point of view, it was MAD2. That means you should see a strong mass and angle correlation. Then what was done in the recent work, that we modified this, where other than the facility, we also included the deformation of the target. Once you put the deformation, include the deformation, you see you are going to MAD3, where you don't expect any mass angle correlation. This is what was recently done. It is published here. So you see how important it is various international parameter. It's not only facility, maybe there's some other thing, I don't know, maybe some other parameter also will be depending. So this is one of the very recent work. I found it's very interesting what they are doing. That if you want to separate between quasi-fission and fusion fission, it is not easy to do from kinetic energy distribution or the mass distribution. But there is a possibility if you measure the gamma multiplicity as it is shown, this is shown for quasi-elastic and fusion fission. That is, you have a quasi-elastic, you have very low Newton multiplicity. But once you go for fusion fission, you see you're getting your multiplicity is very high. So maybe one can now study same compound system with the two different channel and then see the Newton multiplicity for those systems. And one can find out if the system where you expect more quasi-fission contribution, there you should also see the difference in multiplicity distribution. So this is I found maybe this type of work can be taken up. So once after mass distribution, let me also go to precision particle multiplicity. As I told you, what we are trying to understand is whether nuclear matter is a water, like water, or it is like honey, and it is very steep. So how do you do that? Idea is that if this fission is taking place, it takes time slowly, then it will emit more number of neutrons. And if it is very fast, then it will emit less number of neutrons. So you can use Newton as a clock and then find out about the nuclear fission process. So this is a potential energy surface. If you have a compound nucleus in equilibrium is here, and here it can emit a neutron, it can go to fission. If it's going for fission, it has to really in deformation axis. You have to go to saddle point. Once you reach in the saddle point, then only you can this fission reaction will take place. So it's natural from looking from this potential energy plot. One can say that this neutron emission and fission channel are in fact different, and fission will take definitely longer time. So once what you do, you basically calculate the probability of neutron emission. And once you know the probability of neutron emission using Heisenberg uncertainty principle, you can find out the mean time. So depending on the number of neutron, you can find out what is the fission time scale. So one of the very early work was done to study the international effect was this, where you have oxygen, thorium, and boron, neptunium. They are basically systems lying at both sides of the BG point for the compound system. And these are the Newton spectrum with reference to fission axis. And this spectrum were fitted with what is called moving source fit with three terms. One is two fragments and one compound system. So this is a multiplicity. Multiplicity, it gives the multiplicity here. Multiplicity. And by fitting, one can learn about the total Newton multiplicity and pre-component and post. And these things can be also converted to fission time, as I told you, by employing that from this Heisenberg uncertainty principle from probability to mean time. Some of the observation is that your total Newton multiplicity is correlated with the pre. And here you see you have two reactions. One is oxygen and thorium, other is boron and neptunium. They both form the same compound system, but you see their pre-Newton multiplicity are different. That means their reaction times are different. And if you compare with the statistical model, they should go like this. So that's the this is for carbon. And here it is it has been systematized for a large number of system. What he says, when you plot for a very large number of system, you can see you have two lines. One is for same facility, you see you are getting two different times. Certain reactions like if you see the square is oxygen and thorium, and fluorine and thorium, they are here. But if you look here, triangle, is boron and neptunium. They are here. So these two same facility, they are showing different time. And as earlier I saw, your total time has three terms. One is shuttle decision, formation time, and transient time. Transient time is more or less constant for all, around 10 Egypt per second. If you take that, then you see your shuttle decision and formation time are this. And it was concluded that this difference is coming due to shuttle decision time of the compound system cannot be different, but only thing that is different is the formation time. So this was a very nice way to show that formation time for the systems are different. It depends on the entrance channel. So you see, from this study also, it has been extended to high Z element, like 124 Z and 116 and 104. And what you do for various excitation energy around 64 to 74, you get total Newton multiplicity. And when you extend this to zero excitation energy, what you get in this line? This basically says that if you have a nuclei with a atomic number Z104, then it will emit spontaneous fission. If taking place, it will emit 5 neutrons. Similarly, if you have a nuclei with a Z116, it will emit spontaneous fission. It will emit around 10 neutrons. And so for 124, maybe 15 Newton. So this shows that in future, anytime if we are able to populate these super heavy elements, they will be very useful for our making mini reactors. So if the Newton multiplicity is more, then your reactor size can be reduced. So more recently, we also carried out a study on precision Newton multiplicity in sulfur plus tungsten reaction. So this figure shows this is the projectile-like and target-like events when you plot the two time of flight of the fragment 1 and fragment 2. These are the fission events, and for these fission events, angular correlation of fragment Newton correlation energy spectrum were plotted here, and they were fitted with a sim moving source. And what you get is the total time for sulfur and tungsten was around 66, and for oxygen and lead it was 60. And then finally you see, to understand this total time, what one need is your formation time is higher for sulfur and tungsten. If you are taking around 19, and where in case of oxygen and lead it is 9, then only you are able to explain the total Newton multiplicity or total fission time. So this work has been recently published in Physically. So okay, this I told you some physics work we have carried out in a recent past, and I will now take you to some of the application works. Particularly, one of the important thing is the Newton-induced fission cross-section determination by surrogate reaction method for unstable actinide target. So basically, suppose your target is unstable, then you can't you can't make a target and bombard with projectile and do fission. Then how do you do, particularly for a Newton-induced? Because these Newton-induced cross-section for unstable targets are very important if you are going to design a reactor based on fast Newton-induced fission, and also incineration of minor actinides, neptunium, plutonium, lithium, they are in the nuclear waste. So because there will be a lot of isotopes, they will be short-lived. Suppose you need to know their cross-section. So from there only you can estimate how to incinerate them. And also another important use is particularly for fusion reactor. Unlike our fission reactor, where your Newton spectrum is peaking around 2 MeV, but in case of fusion reactor, is the reaction is with the DT reaction, your Newton is 14 MeV. So this 14 MeV neutron, gets bombards the structural material, and it transmutes to various isotopes. And one needs to know their all their cross sections, so that you can estimate the you know um, you can estimate and properly design the reactor. So from all this point of view, and moreover, in our three-stage nuclear program, first we will be using pressurized heavy water reactor with natural uranium. Subsequently, with fast breeder reactor, we will be producing uranium-233, and in third stage, thorium and this uranium-233 will be used for energy production. And this is also nuclear waste transmutation, because fission fragments has got a lifetime is around 300 years, but all these minor actinides, they are 10 to the 4 years, so they have to be transmuted for the safety purpose. So these are the some of the unstable isotope one can see in uranium, plutonium, and thorium uranium fuel cycles. Suppose I take this example here. You have thorium 232. When it captures a neutron, it goes to thorium 233. This 233 will undergo beta decay, and it will be produced 233 protactinium. And again, it will go another beta decay, it will produce 233 uranium. So suppose you want to estimate the inventory that from thorium, how much uranium 233 you can make. It is very important. Want to know what is the NF cross section for 233 protactinium, because this 233 protactinium, its half life is only 27 days, so it is difficult to make a target and then do the experiment. So in such situations, what one adopt is what is known as the surrogate reaction. So you use surrogate reaction is basically, suppose you have a target which is unstable A, and you have a projectile, and you form compound system B, and then fission. But instead of this, you can't have a desired reaction because A is unstable. Then what one can do, one can adopt a totally different reaction. Basically, you do a transfer reaction with totally different target and projectile, but it is such that after transfer you populate a compound nuclear residue which is same as the desired one, and then adopting what is I told you earlier, Bohr hypothesis, that formation is independent of or decay is independent of formation. Employing that rule, one can find out the cross section by adopting that this is a compound nuclear cross section and this is a probability of decay. That decay probability only one has to measure through experiment, and then this compound nuclear cross section that can be calculated from optical model. And when you don't when the dependence of this decay is and this formation is independent of spin and parity, this is called Weisskopf-Ewing limit. So this limit is valid for energies above 10 MeV excitation energy. So, but other than just direct surrogate reaction, recently this surrogate ratio method has been more popular. In this method, the ratio of two cross sections, two compound nuclear reactions for same excitation energy are experimentally determined. Experimentally, you measure two compound nuclear reaction cross section, and then if we independently one of them is known, then other one you can find out. So that this is the philosophy. So one of the early work we did on this is to address protactinium NF cross section. What we did, we took a thorium target and lithium-6 beam. Lithium-6, it is considered alpha and D. And when lithium-6, D is transferred and alpha is going out, what you populate is 234 protactinium. And when your alpha is captured and D is going out, you populate uranium-236. Uranium-236 is equivalent to Newton plus uranium-235, surrogate of that. Similarly, 234 is surrogate of N plus 233 protactinium. So it's interesting in this case is that in a single experiment, by through two different transfer channels, you are able to populate two compound systems. And one of these compound system can be as a normalization for other, because N plus uranium 235 is very well known. Once you know this, then you can always find out this. This is what was employed, and the very first work we did is this. We extended this measurement beyond 10 MeV. And subsequently, employing this principle, we have carried out a large number of measurement of various, many of the isotope in uranium, plutonium, and thorium uranium fuel cycle. And more recently, just recently, also people are trying to do measure not only neutron-induced fission, but neutron-induced gamma. So this is one of the work that has been done for 239 plutonium. But what one can see that these are the experimental point, and this is the modified, calculated, and some of them are from evaluation. But here, because your excitation energy is low, then Weisskopf Younger limit, it is not valid. Then one has to do a real spin parity through a model. You take proper spin parity into consideration, then you are able to get the line, this one, which is consistent with the various evaluation. Maybe more studies can be done in this regard. Also, as I told, we extended the study to fusion reactor structural material. One of the earlier study we did is for iron 55 NP cross section, because iron 55, because reactor structural material is made up of iron, copper, and nickel. Through various reactions, as is shown here, one can get iron, which has half-life of 2.73, and there was no data in this cross section. This was we again did through a transfer reaction, and we this is the work we did compared with various evaluations available in the literature. We also extended this for many other reactions. One is nickel 59 NXP that is published. More recently, we did for manganese 53 NXP. Philosophy is same, but different appropriate target projectile combination by taking, we are able to do all these studies. And then next, I want to also highlight the importance of fast Newton-induced prompt fission Newton spectrum. When you are working with a thermal reactor, what you want to know only the one spectrum, one fission spectrum, that is thermal Newton-induced fission spectrum. If you know, then you know the Newtonics of the reactor. But suppose you want to now design advanced reactor, that means fast Newton-induced fission or fast reactor, or oscillator driven systems. There you need to know your Newton spectrum as a function of incident Newton energy. Basically, fission Newton spectrum or prompt fission Newton spectrum as a function of incident Newton energy. They are very important. And also want to know how your incoming Newton energy is being shared with the fission Newton spectrum. So this is showing one plot. This is for thermal Newton-induced fission. For this, low energy Newton spectrum is not well understood for uranium 235 NF. So this is what is prompt Newton spectrum. Just let me tell something. This is Newton-induced fission. Then it takes to undergo fission is roughly 10 to the minus 20 second. Then from 10 to the minus 18 to 16 second, these fragments emit Newton. They are called prompt Newton Newton, and also they can emit gamma also. So their prompt gamma will come in this time scale 10 to the 4 to 3, and subsequently beta decay and delayed Newton also will come after a long time. So we did this one of the measurement for uranium 238 at our Patia reactor. Using proton beam, we produced secondary neutrons, and secondary Newton was irradiated our uranium target. And then we measure the spectrum. So these are some of the, this is fission spectrum. This is the Newton time of flight. From this time of flight, this is Newton and this is gamma. The Newton spectrum were generated, and they were we want to evaluate this with various suggested level density parameter and total kinetic energy spectrum. And this work is published here. And recently, other than the Newton prompt Newton spectrum, particularly prompt gamma ray spectrum has been very important. Here also we measured for one for thorium. This is compared with californium. This red one is for californium, and this blue one is for thorium. You see there is a difference in gamma ray spectrum, whether it is coming from spontaneous fission of californium or from thorium. Because in case of perhaps in case of thorium, your compound nucleus in case of californium is 98 and this is 90. So your light fragment is having less Newton reach in case of Newton induced fission of thorium in comparison to californium. So that gives less number of low energy gamma ray for Newton induced thorium in comparison to californium. So, but the more of interest, this gamma ray spectrum is recent interest for search for heavy elements production in the cosmos. So, Newton star merger is expected to produce a broad range of heavy radioactive isotopes, and because of this rapid Newton capture, and could emit gamma rays from the radioactive isotopes synthesized in Newton-rich ejecta. These MEV gamma rays may provide unique and direct probe of the Newton star merger environment, as well as insight into the nature of our process. Just as you know, in case of supernova nucleosynthesis, it has been identified that up to nickel 56 signal is there, not beyond. But recently, in case of this is gravitational wave 170817. Optical and infrared observation of this event indicates lanthanide production. They have observed. This has raised a lot of interest to search for gamma rays from this Newton star mergers to identify whether your heavy elements are also being formed. This is a plot of gamma ray spectrum from spontaneous fission of californium up to 10 MeV. But if it is only gamma ray is coming from beta decay, it can come only up to maybe 3 MeV, not beyond. Because our fission fragments are excited, always having excitation energy around 10 to 20 MeV. So our energy spectrum extends up to 8 to 10 MeV. So this using this clue, there has been a simulation has been carried out in a recent paper by in the astrophysical journal letter last month only, where they have shown that if you mix with this YE is basically how much heavy element you mix. 0.15 means more heavy element mix in the ejecta, and 0.3 means there is no. So what it is observed that as a function of time, you see if it is there is no heavy elements or actinides, then all your gamma ray will not see any gamma ray signal beyond maybe few days, 1 to 2 days. But if you have large number of actinides are produced, then they will undergo fission and they will give gamma ray. Then you will see the signals up to 10 to the power 3 days. So this is the detector sensitivity. So it can only detect gamma ray energies, above this. And if basically the light output is above this. And similarly here, this is a plot with the gamma ray energy 3 and above. It has been shown. And if there is a robust amount of um, actinides are there, then you will be able to see that signal. And if it is not there, then you will not see any gamma ray signal beyond 4 eV. So this, this is a good work. Maybe this will help us to more detail. We should study this gamma ray emitted from fission process. This is a really interdisciplinary research. And other than this, I will just highlight the two new facilities that are being coming up in BRC. They are not nothing to do with the fusion fission, but as a byproduct. The reactor is also not only a source of neutron, but also it is a source of anti-neutrino. So it gives an opportunity to study neutrino physics. So, okay, this maybe you all been knowing this in neutrino was hypothesized by Fermi. And the standard model, you have three neutrinos: electron neutrino, mu neutrino, and tau neutrino. So, and there are a lot of most of the study has been done with reactor neutrino in various places. There are certain anomalies. These anomalies can be addressed if we have a experimental setup in our lab. With this motivation, and also further there is a also suggestion of fourth sterile neutrino that can be investigated for a short baseline experiment. And because if you have three flavor, then your line should go like this, but fourth flavor, then only you can explain some of the experimental data. All these things have motivated us to start a new experiment at Dhruva reactor, where we have now in the stage of procuring around 100 plastic detector by 1 meter by 10 centimeter by 10 centimeter, and using a inverse beta decay, we want to identify this neutrino. And this this is useful in the sense this can be also used as to monitor the reactor operation, how much plutonium has been formed from uranium. That can be also done because of this is also a proposal from IAEA to monitor reactors remotely. So this is okay, some of these things. And another new facility we're bringing up at the Dhruva reactor is the Durga facility. Here we also study neutron because neutron-induced fission gives you the most neutron-rich fission fragment. If you are using heavy ions, then you dump a lot of excitation energy to the fragments, and the fragments emits neutron and it cool down. Ultimately, it goes to your N by Z stability line. But if you want to really study neutron-rich nuclei, maybe this thermal neutron induced fission is the right source. So we have a big setup there with the 8 kilowatt detectors and barium fluoride. And this once this facility will be operational, we'll be able to do really nuclear structure studies for neutron-rich nuclei. So I think now I'm coming to the conclusion. Transparency. A few recent results on the international effects on heavy ion induced fusion reaction are presented. Application of fusion fission research in technology development and other disciplines are highlighted. And but still, one question remains: a complete theoretical description of nuclear fission is yet to develop. Thank you all for your patience. So my last transparency is this, where I say there is no dead end in science. It is left to you. It is left to your imagination and creativity to discover something new. Thank you all.
So thank you, Dr. Nayak, for this very exhaustive and wonderful talk. Now there are few questions. I have to first take, let me check from the Zoom and the YouTube. Okay, there is no questions in the Zoom. So there is few questions in the with the
Vivat?
yeah.
Hello, sir.
Hello, Nayak. Excellent talk. I enjoyed very much. I think it took us over a journey of 4 decades or 5 decades of BRC, whatever we did and what you did afterwards. Very, very comprehensive and a very clear presentation. I enjoyed very much. Thank you. Only small thing I wanted to ask, I'm sure you are also thinking extension of surrogate for some nuclear astrophysics for light nuclei. I'm sure we have discussed some time back, but maybe you are thinking about it and you can do it now.
Yeah, no. Yes, sir.
Some astrophysics, nuclear astrophysics related. It will be nice, actually.
Yeah. Even that, I saw that paper. They have recently, it has come in physical review.
Okay.
That gamma and
yeah, that neutron and gamma, as you know, even your reviews of modern physics, that also has some of this.
Okay.
But what I'm saying, that some of the light nuclei, radioactive nuclei,
correct.
which are formed in the stellar evolution.
Okay, that will be great.
Something can be done for, you have done up to manganese. So I'm saying whether you can go a little bit more. The fusion reactions, some of the fusion reactions. Anyway, good. I enjoyed. Thank you.
Okay, there are a few questions in the YouTube. One is by Basav Raj. The question is, how is the time of a nuclear reaction determined?
Yeah, okay. I saw a figure. Let me, can you go to that again? No, I cannot go to the map. I saw, rotation. After half a rotation or 2 rotation, there are measurement for the deep inelastic reaction, earlier days. From this angular distribution, you can find out the time. That is one thing. But what I told today through neutron clock, what you do is by through measurement of Newton, how many newtons are being emitted, and average mean Newton emission time. From there, you can find also particularly fission time scale. But for any other reaction, I know that if you are doing angular distribution, then one has to know that whether it has taken multiple rotation or half a rotation, one can do that.
There is a next question again from Dr. Basav Raj. What is the evidence for the 4th neutrino flavor?
Oh, there is no evidence. It is only prediction. Using 3 flavor, we are not able to explain the low baseline experimental data what you are getting. So then it is natural to include one more flavor. So it's like that. There is no evidence as such, but it's only speculation or prediction. And that is people are looking for it.
Okay, there is another question by Prashant Patil. Sir, how magicity of neutrons of projectile and target related to width of the fission fragments, particularly mass?
What is there? It goes off. No, with magicity. With magicity, once you have a spherical target, this width is not increasing. I think that plot is there in the paper. You can just go back and look that paper. It is there. Because it is not showing any mass angle correlation also. But after including, your deformation, you have brought it to MAD 3 from MAD 2. So maybe if you look that paper by Mohta et al., that will give, width is also plotted there.
Okay. There is another question by Mr. Chetan Sharma. how can we separate the formation time of compound nucleus from the transient time?
Yeah, that I showed you transient time. There is a relation. From relation, you can find out. Again, I will suggest you look into the Alok section of paper. It is very well explained there. Transient time, how he has obtained it is 10 giptosecond for all the system. So it is given there.
Any other question? Let me see. Okay, there is no question. So thank you, Dr. Nayak, and for this wonderful talk. And now I hand over to Professor Bandana Nanal for the
video. Thank you, Dr. Nayak, for a very exhaustive talk, as Dr. Kailash said. I mean, right from the discovery of the neutron, neutrino, and various applications of fission. And I think since this video will remain on available for the offline viewing, many people would really enjoy and learn a lot of things about it. So thank you once again. And thank you, Dr. Professor Bera, for coordinating the lecture. And lastly, but not least important, thanks to all the viewers that even on Diwali, they have tuned in to listen to this interesting talk. And we look forward to your support to IPA activities. So please stay tuned. Next Saturday, we will have a talk on quantum computation by Professor Aditi, same day. Same time, same place. We'll see you there. In the meantime, enjoy Diwali. Thank you very much.
Thank you. Namaste.
Namaste.